Thank you.
Where is that from?
Technology from Kyoto University.
It's here.
Not here. Okay. Okay, so in this talk, we will consider about the Cauchy Dirichlet problem of the first diffusion equation on bounded domain. The equation is given in this form today. The time derivative of u to the power q minus 1 is equal to Laplacian on u. And this talk, we will also take into account of the sign changing solution. So that's why the u to the power q minus 1 is defined in this way. And we impose a homogeneous Dirichlet boundary condition and the initial condition. And okay, so the initial data is taken from this natural energy class and non-trivial one. And Q is supposed to be between 2 and 2 star. 2 star is a Sobolev critical exponent. And the former one, Q greater than 2, corresponds to the first diffusion. Okay. The porous medium case corresponds to the Q less than 2. Okay, so the physical background, okay, so there are several physical backgrounds, but one of them is the stability of asymptotic profiles of plasma diffusion, which was studied by Okuda Dawson. And you can also find some details in the paper of Berryman and Holland in the 1980s. Okay, so the one of significant properties of first diffusion on bounded domain is the following finite time extinction phenomena. So that means for even general initial data, there exists we can uniquely determine the extinction time at which solution vanishes completely everywhere. Actually, and moreover, Berryman and Holland also determined the rate of extinction. Okay, so the norm is bounded from above and below by the same rate. Okay, so T star is the same extinction time. So therefore, if T achieves at T star, the both of them vanishes 0, okay, completely vanish. And okay, so and also that this extinction time is implicitly determined by the initial data. Okay. And moreover, now we can define the asymptotic profile of such vanishing solution. Okay. And actually, the product of U and inverse of this extinction rate converges to some non-trivial function in H10. Okay. And also, it is also known that this phi solves the following semi-linear elliptic equation. So by the way, this phi is called an asymptotic profile of solution U. Okay, so this U. Okay, so this result was first obtained by Berryman and Holland, and then generalized in several directions. Okay. And okay, so now let me explain why this equation appears in order to characterize this phi. Okay. So by the way, this semi-linear equation will be called dP of Dirichlet problem. And actually, now let us introduce a natural change of variables. For instance, we may set this product as V. Okay. And that product is here. And also we stretch time variable to infinite unbounded interval like this. So T S tends to plus infinity correspond to the T tends to T star. So then this rescaled function solves the following rescaled problem. So now we have there appears additional blow up term in the right hand side, and lambda q is a positive constant here. And also initial data is transformed following this rule, right? Okay, so then this rescaled, so this rescaled problem can be formulated as a gradient flow, okay? But it's a bit generalized one because so there appears a time power of V instead of V itself. So if it is just a V, it is nothing but the standard gradient flow. But in this case, we have some generalization here. But anyway, the behavior of solution is somehow very similar to the standard gradient flow. And this function of J is defined in this way, which corresponds to the right-hand side of this equation. And then the convergence of this product to phi is equivalent to the convergence of V to some limit phi. Okay? And also the Dirichlet problem, which characterizes the asymptotic profile, is nothing but the the stationary problem of this rescale problem. So here I let me remark that this equation has a blow-up term. So if we consider the dynamics of the solution for any general data in H10, some solution may blow up and some solution may vanish. Small solution may vanish. But on the other hand, it never happens because we have this estimate. So by multiplying the inverse of this extinction rate, we could get estimate of V from below by positive constant and from above by finite constant. So why such kind of things occurs? So this this comes from the choice of initial data here. Because in the choice of initial data, we have some restriction. Because initial data U0, V0 always has this form. So if we take big U0, so this means that extinction time, lifetime is longer. So as a result, the inverse is smaller. Okay? So finally, the product is not so big anymore. But on the other hand, if we take a very small initial data, the lifespan is very small. But this is negative power. So this one is now very large. So finally, the product of these two things is not so small anymore. So as a result, from the initial data of this form, solution cannot vanish, cannot diverge to positive. As a result, the remaining possibility is converging to the stationary solution instead. Okay. So the class of such initial data will appear later, which will be denoted by script X. Okay, so now let me briefly review the known results, especially for the non-negative solution. Okay. The first one would be global Harnack inequality principle, which is very often used in the analysis of solution to the first diffusion equation nowadays. Okay. So this means the solution B divided by the distance from the boundary is bounded from below and above by some constant. And another important thing is convergence along the whole sequence, whole time sequence, which is proved by Feilreiter and Simonton by the use of the so-called Boyasevich-Simon inequality. And they prove the uniform convergence. And this convergence result is improved by Bonforte-Grillo-Vasquez, which is a relative error convergence. Okay, so it is of course stronger topology compared to the original one. Okay, so now because the phi vanishes on the boundary, so the denominator might vanishes. But on the other, even in this case, this is bounded from above, and also actually it converges to zero. Okay, so now let us move on to the more quantitative study. So this is a very new thing. Okay, so the first one is obtained by Bonforte-Figari in 2021, which they first derived the sharp rate of relative entropy convergence. So that means, so let me explain more details because this result is very related to our studies. So let us assume that phi is non-degenerate, so which means the linearized operator, which is nothing but the second derivative of the energy functional at phi, is invertible, has no zero eigenvalue. So then this quantity, it seems like a weighted L2 is decays at this rate, explicitly this rate. And okay, Q comes from the equation, but the new K denotes the least positive eigenvalue. Because the phi is a saddle point of functional J. So linear operator always has negative eigenvalue. So therefore, the new K denotes the least first positive eigenvalue. And in their paper, they also explained the, how should I say? So this rate is sharp in a certain point of view, which is based on the formal linearized analysis. Okay. And then the Jin and John also derived optimal boundary regularity theories. Okay, so which so at the first glance, it is not so related to the asymptotic behavior, but actually it is very strong. It implies a strong conclusion. indeed, if we use their optimal boundary regularity results, we could improve the topology of convergence somehow. And myself, I derived the same late convergence, but in a Sobolev space. And also the method of proof is very different. So in the paper of Bonforte-Figari, they developed a nonlinear entropy method. On the other hand, in my paper, I used the energy method, something like energy method, which will be explained in this talk. But anyway, so in this paper, I also derived some the convergence with late even for sign changing solutions. But the late is a bit less than this one. So okay, it is not sharp for the sign changing solution. Okay, so now let me also recall the results by Choi, Mak, and Saxo. Choi is here, yeah, right? So they proved the rate of convergence to possibly degenerate the asymptotic profiles. Okay, so in the last slide, in both results, we assume the non-degeneracy of the asymptotic profiles, but their results can be applied for possibly degenerate asymptotic profiles. So then there's a following dichotomy follow. The first one is the convergence rate is faster than the sharp rate, which we discussed. And the other one is the convergence is slower than S inverse. And moreover, phi is the so-called ordinary limit, which means the kernel of the linearized operator can be characterized as a stationary solution. So then the convergence is still, again, exponential first. But okay, so based on these results, there still remain. We found the following open questions. Okay, the first one is that many issues on sign changing solutions are still widely open because of the lack of regularity theories. For instance, in the previous results established for non-negative solutions, because most of them are based on the global Hannock principle. It is a basic and quite important device. But on the other hand, it never holds true anymore in the sign changing solutions. Okay. And the second one is the optimality of this rate. Okay, of this rate. And actually, in the paper of Bonforte-Figari, they explained why this rate is sharp in view of the formal linearized equation. But there, to the best of my knowledge, there has been no results that where on the existence of certain initial data for which solution actually decayed in this rate. So that means estimate from below by this constant. Okay, so this is the second question. So today I'd like to give answer for these two questions. Okay, so this is based on the joint work with Yasunori Maekawa. Throughout the following result, we always assume that omega is now general bounded domains, okay, without any regularity assumption. And Q is between 2 and 2 star, and U0 is like this at the beginning. And V is now possibly sign changing solution. Okay? We don't need to assume non-negativity. And suppose that Vs converges to phi, and phi is non-degenerate. That means the linearized operator is invertible. Okay, so first result is the following. It is a complete extension of my own results, okay, to the possibly sign changing solution. So in my last paper, this rate was slower, okay, but now it is same as the non-negative solutions. Okay, so the J is the energy functional, which appeared in a generalized gradient flow. Okay, so the relative energy converged to this rate at this rate, and which implies that Vs converge to phi in H10 explicitly this rate. So and the new K is defined in the same way, and linearized operator correspond to this one. Okay, by using these results, we can also prove the following. Okay, so by the same assumption for phi, but now we also assume that phi achieves the least energy among the all non-trivial solution to the Dirichlet law. Okay. And also take EK, be an eigenfunction for the linearized data corresponding to the least positive eigenvalue. Okay. And then we will take initial data in this form. Okay. So then we could get the estimate from below by this rate, even for the relative entropy. And this can be also estimated from above by Sobolev norm. And in the first result, this is bounded from above by this one. So now it is in the original variable, we found out that U of xt, the first term of the expansion is like this by Berryman-Holland results. But now we could also find out the second term decays explicitly at this rate. Okay, not for any data, but for well-prepared data, the second term explicitly decays this rate. Okay, so in the rest of time, let me explain how to prove it. Okay. Okay, so for simplicity, we may write U to the alpha instead of this one. Okay, so this is an energy method. So the strategy is always same. So let me recall our equation, the scale problem. So this is time derivative of v to the 2 minus 1 is equal to minus gradient of energy. Okay, so this is our equation. So in the energy method, we test this equation by time derivative of v. So then in the right-hand side, from the chain rule formula, we immediately obtain the time derivative of the energy. And as for the left-hand side, okay, so here the power of v is q minus 1. But on the other hand, we test simply time derivative of v. So that's why the conclusion has different power, in a sense, mean of the powers. Okay. But this is not happy because this term never appeared in our equation. Okay, so that's why we want to rewrite this time derivative with different power by the same power as the original equation. Okay, and actually we can expand it in this formula. Okay, so now let us substitute this relation to here. So so this L2 norm comes here. Okay, so this is the strategy in my original paper for the possibility for positive solutions, non-negative v. Okay. So here, by substituting this relation here, so then the time derivative of v to the power q minus 1 appears. This is exactly same as the left-hand side of the rescheduled problem, right? Okay. But on the other hand, there appear the strange reminders with negative power. So I don't like it. So that's why I decided to divide it by 5 and put 5 to the power 2 minus q. Okay. Now it is very nice because this can be move it away from the integration by taking L infinite norm because this is negative power. But this is nothing but the relative error conversion. So this uniformly converges to 1. Okay. So then the what remains is L2 norm of the time derivative of v to the power q minus 1 with some singular weight, but this singularity is only on the boundary. So we can somehow manage. Yeah, it's doable, right? But it is limited only for phi positive. So that's why I had a problem. And I couldn't find how to do it, yes. And then, okay, so I gave a talk on this result in the Kyoto University, and Yasunori was also there. And after the seminar, we exchanged some email a couple of times. And one day he wrote me and some email. Why don't we leave it as it is? So at that time, I was hit by thunder. Okay, it might be a good hint. So I decided I will leave it as it is. We don't do anything like this. Okay. Of course, we have to face some new difficulties. That is, we have to consider the strange weight function, strange L2 space with weights, singular weights. And this 2 minus q is negative, right? And also v is sign changing. So, of course, there appear some delicate motors to handle with such a weighted L2 space. Okay, but okay, so today let me omit the detail. But anyway, if we use such a strange time-dependent weighted L2 space, we can rewrite the formal relation like this. Okay, so this weight function space is still time dependent, and it is also weight is still singular. But on the other hand, we are happy because now time derivative of v to the q minus 1 is nothing but the time fresh derivative of j, and this is derivative of j. So in a sense, this inequality is only concerned with j. Okay, j and the fresh derivative of j. Of course, there still remains a problem how to connect the j and its fresh derivative. But anyway, now we somehow can be related to derive the differential inequality only with j. Okay. By the way, if we don't like to use such a crazy weighted function space, we have another option to handle. So that is the following. So instead of this inverse weight, we may add some minus Laplacian plus v to the q minus 1 and take inverse. Now this is a good operator, right, in the functional analytic point of view. But on the other hand, in this case, we have to control the error coming from this kind of thing. So we have now two ways. The one is directly handle this crazy weighted space, but the other one is admit errors, okay, approximation. But anyway, so today let me focus on the formal one. Yes, yes.
The weighted space with 2 minus q is not the natural one for the second variation of the operator?
Yes, it's natural. Yes, that's the point. Yes. So we will consider the linearized operator at j. Okay, yes, that's right. Yes. So this is this one, right? So in order to derive the relationship between the energy and its fresh derivative, the following lemma will be used. So this is nothing but the quantitative gradient inequality, which was developed by myself in my last paper. Now it's more dynamic because in the last paper, I derived this inequality by taking a linearized operator at phi, but now I may take a second derivative of v at v of s. But anyway, the derivation of this inequality is more or less same as my own paper, last paper. But then there appears some problem that now the eigenvalue also depends on s. But it can be managed by using the so-called Rayleigh-Ritz variational principle, so which can characterize the eigenvalues. Okay. By using this formula, we can estimate the difference of the eigenvalue of linearized operator at phi and that at v of s with quantitative information. Okay, so now let us combine these two things. Okay, as the first step, we derive this one, okay, by taking a crazy weighted space. And the second step, we derived, so this is the conclusion of dynamic quantitative gradient inequality. And these two quantities are same, okay? And this one, by combining these two things, we can derive the differential inequality only for energy. So this is nothing but this one, okay? And then, okay, so this is the error. But by the way, this error is characterized as in terms of only H10 topology, okay? Because originally I used relative error convergence. So in this case, we need more delicate regularity estimate, and which may lose its information at the initial time because this is smoothing effect. But this is not a smoothing estimate, right? So this can be finite even from the initial moment. So we could get some estimates. And finally, by solving this simple differential inequality, we can derive the exponential estimate. Okay, so this rate is still non-optimal, but we can, so in order to get the sharp rate of convergence, we needed to quantify this error more carefully. But on the other hand, it has already been done here. Okay, by the way, in order to derive the convergence of the energy gap, so from the convergence of energy gap to the Sobolev convergence, this time we developed some coercive type estimate. In my last paper, I used a slightly different argument, which is very often used in the context of gradient flow theory. But this time we also developed a slightly different estimate. But anyway, so from this estimate, the Sobolev norm convergence directly follows from the energy gap convergence. Okay. Okay, so now let us move on to the optimality results. Okay, so in order to derive the optimality results, the following corollary will be used. So this corollary is immediately follows from the first result. Okay, I also derive the similar exponential. Okay, so first let me explain the results. Okay, so this is the exponential stability of this asymptotic profile, which means if we take initial data very close to the target, so then B of S again converges to phi. And the rate of convergence is the same as before. Okay, and this is a constant. And of course, in this case, we have to take initial data from the class of initial data which I introduced. Otherwise, some solution may grow up or extinct. But by this choice, we could get the exponential stability, even if phi is the saddle point of J. Okay, I also derived a similar exponential stability result in my last paper. So what is the difference? The difference is this orange part. So this constant of the exponential stability can be controlled by the initial energy gap now, okay? Because it is possible. Because in my last results, okay, so this, so how should I say? Okay, so even in the proof of this theorem, this differential inequality holds for S apart from 0, okay? Because we handled general initial data. But on the other hand, if we take initial data very close to the target, so then by using my previous result with Ryuji-Kajikiya, we could get qualitative asymptotic stability result. That means this quantity can be somehow controlled by very small constant from initial time. Okay, so by using these results, we can finally get this inequality holds true for any S greater than or equal to 0. Not instead of S lambda, we can put 0 here. So therefore, we can integrate both sides from 0 to S. So then this one can be replaced by BS0, so the initial data B0 and J5. Okay. So that's why we could get we can specify this constant. And this helps us to get optimality results. Okay, so now let us move on to the proof of optimality data. So let us take this initial data, but which is still outside of our set of initial data. So we multiply certain constant, so that then this lies on the X. So X is something like a ball in the H10 space, unbounded ball. Okay. So then, since epsilon is very small, that we could take C epsilon sufficiently close to 1. But anyway, it is still different from 1. And therefore, if epsilon goes to 0, this initial data converges to phi. Because if epsilon goes to 0, C epsilon converges to phi, and U0 epsilon converges to phi. So as a result, V0 epsilon converges to phi. Okay, so now let us subtract two equations. One is the rescaled problem, and the other one is the equation for phi. Of course, the time derivative of phi to the q minus 1 is 0. So this is done. And then now let us act okay, so the point is the following. So the point is how linearize this equation. This is the point. Okay? Even for Okay, yes. Then in this paper, in this work, we first multiply the inverse of minus Laplacian in each term. Okay, and take this quantity by Ws. Okay, so then we have this inequality, this equation. So now minus Laplacian disappears because we acting minus Laplacian on both sides, each side. Okay. And then now let us act spectral projection corresponding to the least positive eigenvalue nu k, and denoted by the exponent component by wk of s. Okay. So then, okay. So this is almost the same. Okay. But the problem is the following. Now we are focusing on w. Okay. W is consists of the v to the power q minus 1. So in view of, from the viewpoint of w, v minus phi is now nonlinear term. So here we would like to linearize in terms of that. Okay. But by using this spectral projection, we could derive certain very useful relationship, which exactly derives the linearization. Okay. Actually, the Vs minus phi is replaced by rewriting in terms of W with some error. Okay. So error, of course, appears. And then finally, we obtain this differential equation, even without any special derivatives. Okay. This is just ODE with unbounded operator. And also we can derive that this remainder term can be controlled from above by this quantity. Okay, okay, so now let us solve this ODE by using Duhamel principle. Okay. This is that one quite standard thing. Okay. And now let us estimate this quantity from below by using a triangle inequality here. Okay. And now the point is how to control this remainder term. And also we have to take into account of the estimate of this remainder term from the initial moment, because this is Duhamel integral, right? But now we have full information about this quantity from the initial moment. And even this term can be controlled by the initial gap. Okay. So if initial data is very close to this quantity, this constant is very small. Okay. So as a result, we can prove that the first term is stronger than the other one. Okay. Naturally, this one, okay, so this comes from here, and by using this estimate, okay, so the point is, we also have another point. Okay, so this error term, remainder term has a bit stronger decay rate, okay, a bit stronger power. And also we have a sharp rate of convergence. So by combining these two things, this one, so maybe this should be plus, sorry, this should be plus. Okay, so this can, finally, this exponent can cancel in a sense, and this integral is integrable. Okay. And so, okay, so this exponential rate is used to prove this integral is finite only. But we have to squeeze this term by taking initial data sufficiently close to phi. Okay. So that's why this information is really, really necessary in our analysis. So finally, we can conclude that this quantity can be estimated from below by epsilon times the exact rate of convergence times for sufficiently small. Okay, thank you very much for your kind attention.
A lot of very interesting talk. Questions or comments? Please.
So at some point, the proof you multiply by some C epsilon, which is the one. Is this, in other words, a way to recenter your data on the stable manifold of your?
Yes, something like this. Yeah, something like this. So naturally, in a sense, okay. So if we consider the energy space, yeah. So this is H10, and this is origin, and this is our set X. Okay, X. And all stationary points are lying on phi in a sense. And if we take an initial data V0, well, we take a some ray and take a projection on B0. Okay, so this is nothing but the CF silent U0, CF U0, something like that. And by the way, this set X plays a role of separatrix of dynamics. So inside this separatrix, solution goes to 0, and the outside solution diverges to plus infinity.
And we may have a second one. So in certain sense, you are redoing some part of the proofs in the stable manifold theory. What prevents you to apply the theory directly? Or maybe some technical problems?
I think the characterization of X is very implicit. So as far as I know, the X is just a level set of T star is equal to 1. And the T star is the extinction time corresponding to the initial data. And we know the continuity, but at most continuity, you know, and yeah, that's why we can.
So after you do the analysis, can you improve what you know about X, capital X?
Capital X.
Posteriori, can you know more?
As at this moment, we didn't get extra information from this analysis at this moment, unfortunately. Yeah. But so maybe the analysis of X is more related to the well-posedness results or something like that. Yes, because so how should I say? For instance, the continuity of solution depending on initial data or something like that. These kind of things, if we could quantify these results more, so then we can get more information.
So is X kind of set with codimension 1?
Even this, I have no idea, unfortunately. But maybe yes, maybe yes.
Because I thought the codimension of X should be equal to the number of unstable eigenfunctions
Yes,
to
yes,
your
yes.
linearized operator.
That's
And I think we don't have no idea the
At least-
dimension of this unstable part.
yes, maybe yes, but I haven't. Yeah. Because even if the smoothness of the surface is clear and it is just a level set of continuous functions, this may include a monster, right? So that's why, yeah. But anyway, for instance, Nehari manifold is given more explicitly, and the Nehari manifold has the codimension is just only 1. And we could also derive the relationship between this set and the Nehari manifold. But anyway.
And I have one more question about the assumption on the theorem 2, that you assume it's least energy with non-degenerate, which
Yeah.
somehow means the phi has to be an isolated minimum in the space of critical points.
I think isolation comes from non-degeneracy directly, but least energy means how should I say? Okay, so it comes from this part. Okay, so the least energy asymptotic profile is stable. So this means that even if we add certain perturbation, the V can come back to phi. Yes. Okay, so this may be a very delicate point in the study of first diffusion equation, because in the porous medium equation case, phi is completely the minimizer of energy functional. So even if we any perturbation solution come back to phi, positive solution. But the first diffusion case, that this is already saddle points. If we put bad perturbation, the solution cannot come back here. But in the least energy solution case, it can come back.
So my question is there any case when we have such a sign changing such a solution?
Yes, that is problem which we want to consider, but not necessarily.
Oh, sorry.
Yeah.
Okay.
The problem is very, how should I say, very, so if we could extend this result, of course, all sign changing solutions are unstable. We could prove it, but somehow, if we could, even if the phi is completely unstable, even on the set X, if we could construct a good perturbation for which the solution come back to phi, in this case we can. But,
so at least so sign changing guys are not least energy.
The sign changing solution is not. All least energy solutions are positive solution. Yes.
When we began working on these separation variables and so on in fast diffusion, I had this problem that an engineer posed me. What happens if your domain is a rectangle?
I think a rectangle is okay now. It's because we don't use any regularity theory. We just use, say, sovereign code and so on, and everything is considered in H10. The extinction operator can be defined any domain. So this is also one of the advantages of this proof. So we. Yes.
Okay.
John, please.
Yes, on the previous slide, on the synthetic stability result, here you have a dependence in the difference of the energies.
Yes.
The C, does it depend on the initial datum as well?
No. She is independent. Yes, at least on the neighborhood of 5. Yes, of course.
Yeah, okay, so you have a smallness assumption there.
Yes. Otherwise it doesn't. But yes, and also V0 lies on this phase set X.
So which means that for the coercivity estimate, we would get a stability result, but only on a local level.
Stability results. So what do you mean? Sorry.
Well, okay, you can look for the optimal cases of this thing, and then you would eventually get some
Coercivity.
remainder term.
Okay, remainder term means the further extension, right?
Well, I mean, using the flow to get stability.
Not sure. Sorry. So maybe we may discuss later. I'm sorry.
The question. Sorry.
Please. Then one last question and then we are.
I have one question. Somehow your result is stability problem. Okay. So for the stability problem, it be more interesting if we consider on whole domain, and how about your problem on
So whole domain means Rn.
Yeah.
Yeah. Okay. So the behavior is totally different in the bounded domain case and the full
So
domain.
and in this case, you don't have spectrum gap, and mu k should be equal 0. Is it correct? Then you
New K is positive one.
Yeah.
Because this is a first positive eigenvalue. That is positive, of course. This is a kind of spectral gap.
Oh, if mu k in the on whole domain it is still positive, and you still have
Okay, the whole domain case eigenvalue is not right. So the spectral is continuous.
okay,
Yeah.
I see.
So of course we can consider the strict domain case. In this case,
Yeah, that's
behavior
why later on,
might be different. Yeah.
somehow the analysis, and you still have
Yes. In this case we can, but the difference though.
Yeah.
Because in this case there also appear the non-compact behavior solution.
So for the stability problem, very different between on-bounded domain and on-whole domain itself.
Yeah, very different, because in an unbounded domain case, the solution can preserve, sometimes, in some cases, the solution can preserve mass like a heat equation. In this case, no solution vanishes, right?
Yeah.
So because in this case, it is a bounded domain and the Dirichlet boundary condition. So Dirichlet boundary condition implies a singular diffusion. So that's why the diffusion process accelerates. Yeah. So,
Interesting.
Okay. You have any other questions?
Just a couple of questions.
Yes.
First, I think that what Chan was asking, but I think that what Chan was asking if the constant C depends on delta zero.
Delta zero.
Yes, the constant C in the estimate.
Yes, yeah. Of course, it depends on phi and delta zero. Yes, of course.
So it was, I think this is what we were
Okay,
interested in, because it's the closedness
Yes,
implies.
it's really necessary.
really
Yes,
necessary.
and also in this case, pi should be least energy one. Otherwise, it
Yes.
doesn't work.
And then I wanted to ask you, when in the end you define this exponent rho, and you have rho plus 1, no, at the end when you do the count,
This one, right?
Yes.
Okay. It is actually 2 for q greater than 3,
Also,
but q less than 3, there
Yeah.
appear the non-lipschitz functions and
yes, okay, so but this is, okay, always bigger than 1, right?
No. Rho is not greater than 1 in a sense. Yes, because if so this is precisely given by the maximum of q minus 2 and 1, minimum of q minus 2 and 1.
In the next slide is, sorry, but you
Yes.
take rho plus 1 divided by 2, and this is.
Okay, so maybe I made some mistakes maybe, so somewhere. I should,
No,
sorry.
because if it's not bigger than 1, then it's not lower order.
No. Yes, this is bigger than 1, right? So because this, okay, so I didn't explain, sorry. So the smallness of this one can be controlled from above by epsilon square.
Ah,
So that's why this one is, sorry, so this isn't wrong, sorry.
Okay.
Low plus one,
Okay,
yes,
okay,
I'm very
okay,
sorry.
okay.
I'm very sorry.
Yeah.
You are right.
Okay, thanks a lot to Professor Lacainte again. Right, we immediately go with the next talk, please.
What name?
We start. So if you need some time, just talk. Okay. Couple of minutes. Not hurry.
Okay.
Really very well.
Ah, this is it. Okay, yes. Yeah. It's very close to our. I think it might be
You know what works? There is the pointer, there's left and right, no, left and right, okay, people. Understand? Okay, so let's start with the next talks. Professor Stan from Universidad de Cantabria will talk about finance and topic behavior for the fast Laplacian evolutionization. Thanks, Diana.
Thank you very much. Thank you very much to the organizer for inviting me to this workshop. I'm very happy to be here. We talk about the fast Laplacian evolution equation. My talk is similar to the one of Professor Lacainte, since I will talk about the asymptotic behavior of solutions to a fast diffusion equation, except that I will do the case of Rn. Let me comment that the results that I will explain for the fast Laplacian equation, they are also available for the case of the fast diffusion equation. Some of them, they are already done, and I can show you references. So let me start. This is the motivation for our work. Let's start with the heat equation, and we take so the heat equation in all space, and the data to be integrable and bounded. So we know that the asymptotic behavior for large times is given by the Gaussian function with the same mass. So we have that U tends to the Gaussian in LQ non, for instance, when Q is from between 1 and infinity. So this result is known. And if the initial data has a finite second moment, then there is also a rate of convergence. So here, this is the L1 node, and then the difference. So the case like well, less than this negative power of time. And when you take the convergence in L infinity, since both the U and the Gaussian, they decay to zero at when time goes to infinity, then you need to multiply with this correction there, so that you can see something in this difference. So when you multiply with this, then it's not obvious that this quantity converges to zero, but there is a proof that it goes to zero with this rate. And now let me put the following question. So the previous result, does this result implies that the quotient between U and the Gaussian function tends to 1 uniformly in Rn? If you remove this L infinity, then of course, since U tends to the Gaussian, then the quotient tends to 1. But you want this convergence to be uniformly for x in Rn when time goes to infinity. And the answer to this question is that, well, it doesn't happen always. And the difficulty is at infinity, because when x goes to infinity, both U and the Gaussian, they go to 0. So the quotient is not obvious that it converges to 1. And there is an easy counter example that I found in I put the reference here and it does not appear. So there is yes, there was a reference here that I don't know what does appear. So there is a preprint of Palme's practice on arXiv about the heat equation. So he constructs this easy, I mean, he makes this easy observation that if you start with initial data, which is also the Gaussian translated, so now it is an L1 function, then the corresponding translated Gaussian, okay, so T plus C at time, this is the solution with of the heat equation with this data. And then you take the quotient between this U here and the Gaussian, okay, you subtract the -1 and you obtain this, this quantity here, okay, this one. And this is not uniformly bounded for all x in Rn, because you still have this exponential term here. So it is not true that you can prove this property in this simple example. So for the heat equation, we don't know how to answer to this question. So which is the optimal class of data, so that you can say that the quotient between the solution to the heat equation with initial data U0 and the Gaussian converges to 1 uniformly in Rn. But for nonlinear analogs of diffusion problems, the problem is solved. So for instance, take integrable and bounded initial data. And if you consider the fast diffusion equation, M, it's in the good fast diffusion range, so less than 1 and larger than the conservation of mass range, then convergence in relative error has been proved by Palme's. Then global arc principle by Borforte Vasquez in 2006, under some decay condition, pointwise decay condition on the data. And later on, a complete characterization of what it is the global arc principle and convergence in relative error. So convergence in relative error is this thing, that the quotient between U and the corresponding fundamental solution of that PD converges to one uniformly in R. So this is convergence in relative error, and so I will call it this way. Okay. So for the fast diffusion, there was a complete characterization of these properties by Bonforte and Simonov recently, and they also considered fast diffusion equation with some Cafarelli or Nirenberg weights. Okay. In what follows, I will explain to you what is the global arc principle, since I will explain this result for the fast Laplacian equation. So now I just want to recall some previous literature. So another surprising result is that even for the heat equation, the classical heat equation, the convergence relative error is not known. But for the fractional heat equation, This is the same, it's a linear problem, but the operator now is not local. When the convergent relative error, it is proved, and there is a reference by Bonforte, Sire, and Basket. And also for the fractional P Laplacian, no, sorry, for the fractional P Laplacian also, there is another reference. So now this is our result for the fast P Laplacian equation that I want to explain in this talk. And we take the fast diffusion range, P less than 2, and larger than the conservation of mass range. Okay. So these are some examples. There are more examples in the literature, but this is what I wanted to mention here. And in our paper, you can find much more references and complete. So you can find the complete references. Okay, so this is the problem we consider. This is the evolution equation for the P Laplacian equation, and we take the Cauchy problem. So with a data, which is L1. Then we take P, so with less than 2 and larger than this conservation of mass range. And this is the P Laplacian operator. This is the fundamental solution called the Barenblatt solution. Most of you already know this function. So I draw here a picture since I want to emphasize that in the fast diffusion range, the Barenblatt solution, it is positive everywhere. So the equation has the property of infinite speed of propagation. That means that even if you start with data which is compactly supported, then immediately in time the solution will be strictly positive. So this is the Barenblatt solution. This is the first time, and then when time evolves, then in the middle it goes down, but the tail goes up, so that it verifies the property of conservation of mass. It is proved in it's a first reference by Camin and Vasquez that the solution of the Cauchy problem with initial data U0 converges to the Barenblatt solution with the same mass in L1 and also L infinity when you have to add this correction term here when time goes to infinity. And we found the proof for P larger than 2. This will be the slow diffusion case in a paper of Camin and Basket. But then for P less than 2, the result is known, but we didn't find a proof written, so we proved it ourselves in our paper. So now we are interested that given this result, can you say that the quotient between U and the Barenblatt solution with the same mass converges to 1 uniformly in Rn? This is our purpose for this talk. So we address the following question. Do non-negative integrable solution behave like the fundamental solution? And if yes, in which sense? So we saw before that there is a convergence for the difference in L1 and L infinity, but we want more. So we want the quotient converge to 1. And this will have the consequence that U and the Barenblatt will share the same tail behavior. So when x goes to infinity, when both of them go to 0, we want to prove that you share the same tail as the Barenblatt solution. So we will prove our result in an optimal space for the initial data, and this will be a space that we call XP. And this space contains functions which are integrable, but not all integrable functions, so that if you see only the tail, so you integrate when x is larger than r, and then you multiply with this power of r, so you want this quantity to be finite. In this way, it is a little bit difficult to see this space, but it has a subspace which is easier to understand. So a subspace is contains the functions, integrable functions, such that these functions, they have a tail which is so faster than this negative power of x. This negative power is exactly the tail of the Barenblatt solution. Okay. So AP is a subspace of XP, and it's not the same. So we can construct an example of a function in XP which is not in this space. Then this space is not trivial. The Barenblatt solution is here, so this is the tail decay. And of course, you can find compactly supported functions. So we will prove that this will be the optimal space for initial data, such that convergence relative error holds for the evolution P-Laplacian equation. This is our main result. So we take integrable initial data and also positive or negative, and U to be the solution of the Cauchy problem for the P-Laplacian evolution equation. Then we prove that these following three statements are equivalent. So the first one will be that the initial data belong to the space XP, and it's not trivial. Okay? So I recall here the definition of the space XP. Then the second one is what we call the global Arnold principle, which says that for some positive time t0, you can sandwich the solution U to the P-Laplacian between two Barenblatt solutions with different masses than U. And then you can also have to make some translation in that. But the idea is you can represent U between two Barenblatt solutions, and these are explicit functions. So this way you have a quantitative estimate of U from below and from above, both in space and time. And the first statement is the convergence relative error, which says that the quotient between U and the Barenblatt solution with the same mass as U and at the same time t, this converges to 1 uniformly in Rn when time goes to infinity. So we prove these three statements are equivalent. What happens if the initial data is not in the space XP? So this proves the, let's say, the optimality of this, let's say, integrable take condition space. So we construct some counterexample of data which is not in the space XP. So we take some U0, which has a decay which is faster, so from above, than the decay condition that we impose in the space XP. So this data decays faster than, let's say, the decay of the Barenblatt solutions. And then, so with this U0, you will have a solution to the P-Laplacian equation. And in order to estimate this solution, we construct some sub-solution and some super-solution corresponding to this type of decay. And then we can track U between these two type of estimates, which proves that U has a decay which is above the decay of the Barenblatt solution. So this U does not share the tail of the Barenblatt solution, so the convergence relative error is not true in this example. Okay? So this proves that here we need to take the data in the space XP, otherwise we cannot prove this quantity or this quantity. Okay? So you will not share the same tail as the Barenblatt solution. Okay. Some other some applications of this main result. So I already mentioned the uniform convergence relative error, which was the third statement, but this is a result which is important itself. So I put it again here. Then another consequence is that you can prove convergence rates. So we knew before that U converges to the Barenblatt in L1, but we knew that this difference goes to 0. But you can also prove rates of convergence. And this is something which was proved by Aguilar-Shecarillo or Delpito Dolbeau, but they consider a more general evolution equation, which is a doubling nonlinear, which is this one. So Laplacian apply to U to the M. So if you take M equal to 1, this is the P-Laplacian. See, they already proved this result, but they consider a very strong hypothesis on the initial data, which is something that which is something stronger than the one we consider. What we do, let's say, we find the optimal class of data such that after some time, our solution will be in the hypothesis that these papers consider. Okay, so then you will have the rates of convergence. Some other applications, quantitative stability results in Gallardo-Nirenberg Sokolov inequality. There is a paper of Bonforte, Dolbeau, Nazareth, and Simonov. And some other applications, and this is something that I used in my PhD thesis, for instance. I mentioned also Aldrito and Vasquez for Babin nonlinear. What I did with Juan Luis in my thesis, we took a fractional reaction diffusion equation, and we needed the global Arnaud principle. In fact, we needed quantitative estimates from below of the solution of the pure diffusive equation in order to estimate the behavior of solutions to a reaction diffusion equation. This is an application that I found previously in my research. I want to make a comment about the local Arnaud estimate. So most people know the local Arnaud estimate. For instance, for the P-Laplacian, this was proved by Monforte, Yacar, and Vasquez. So this says that if you take U in a ball, then the infimum it is larger than a constant by the supremum of U in a ball, and the constant is independent of the ball you consider. So this is the local Arnaud estimate. If you want to write this for the whole space, so if you want instead of the ball to put here Rn and this Rn, then this quantity is 0. So the infimum of U in Rn is 0. So then this estimate in Rn does not say anything. So this is why we call global Arnaud principle this formula of estimating, of trapping U between two fundamental solutions which are explicit. So now I want to say something about the proof of this main result. So I start with some ideas for the proof, and then I will explain at least what I have found here. So some properties of solutions to the Laplacian equation that we need in the proofs. Okay, so this result were already proved. Exists the same uniqueness of fixed solutions for L1 data. Then there is conservation of mass. The mass at time 0 conserves for all positive time. Then what was very important was the infinite speed of propagation, compactly supported data. Also positive, so positive compactly supported data produces everywhere positive solutions. And another estimate which was very useful, that the time derivative of U can be estimated from above by the solution U divided by this by a constant and T for all positive time. And a consequence of this is that if you take T to the minus 1 over 2 minus P, so this negative power of T multiplied by U, this is a non-increasing function. And this is something that we really used to obtain some estimates in the paper. And another estimate is the smoothing effect, the L1 L infinity smoothing effect, which says that the L infinity norm of U can be bounded by above and be estimated by a negative power of T0 multiplied by some constant, which depends on the initial data. There is also a local smoothing effect by taking here a ball, but the estimate here is quite more complicated to write, but you can find it in our paper. So I want to give some ideas about the proof of the global Arnaud principle. This is the upper bound, that if you start with the data in the space XP, then you can put from above a Barenblatt solution with a different mass and the translated time. And these are the main steps of the proof. So first we start with data in this complicated space of integrable tail condition. And then we can prove that immediately in time, for some time, immediately in time, we can prove that U, in fact, has a pointwise decay, so that U can be estimated from above, but this by this negative power of X. Okay, and then this says that U at this posterior time that I just write for practical computations, T0 over 2. So this belongs to this subspace AP, which are functions that decay pointwise faster than this power of X. And this space is much more friendly to work with it, since this power, this is the tail of the Barenblatt solutions. So once you know that U decays like this, it is easier to put a Barenblatt solution from above. So now our purpose, our objective is to prove that you can put a bottom block solution from above of a solution to the P-Laplacian with data in the space AP. Okay? And then you go back to U using the semi-group structure of the P-Laplacian. So this is an idea of how to put a bottom block solution from above. This is our solution yield. Okay. And we know now that the data decays faster at infinity than the bottom block solution. So we take U, and then at some point here we cut, and we construct something which is called a singular bottom block solution, which is a modification of the bottom block solution, and it's a function that when x goes to 0 goes to infinity. This is the blue one, but it has the same tail decay as the bottom block solution. So then we are able to put this from above, since you already had this decay at this time t0. Okay. Then this blue function at some point will meet an upper bound, which is a constant, which is given by the smoothing effect for the solution u at time t0. So it meets this orange barrier from above. Okay. And then in this point, you can make computations so that you can put the bottom block solution, the green one, from above this blue point. Okay, so then outside the bottom block, you can construct it to be larger than this blue one. This is easy to do since they have the same tail. And then here you ensure that this point is above this blue one. And then since the bottom block solution is the function as before, which is radially decreasing, then inside it will be above this ray point. So it will be above the barrier given by the smoothing effect. So this is the way how you put the bottom blocks from above. Okay. So this is an idea of the upper bound. And maybe I go a little bit fast. So now this is the lower bound. So now I want to put the bottom blocks from below. Okay. And here the key point was to be able to prove an estimate for you in a ball. And this estimate, we want to prove it quantitatively in terms of the radius of the ball and time. So we were able to prove this estimate here. And then we put a bottom block solution from below U inside the ball. And outside the ball, we were using parabolic comparison principle. Okay. This is more technical to explain than before, since I didn't put any picture of this. Okay. But this is the idea. First, you start with the ball and try to estimate U as better as you can in terms of the radius of the ball and the time. And then, since we proved the upper bound in terms of the bottom block solutions and the lower bound, then we want to prove the convergence relative error. Okay. So we want to prove that the quotient between U and the bottom block solution converges to 1 uniformly in Rn. So the idea is to split the parabolic space in two regions. So this will be Rn, and this will be the time. You have the time, and then you construct some cones. And here will be X. I want to write it there. Okay, so you have some interior cones. Something like this, and this will be X less than T to some power. Okay, and then this is the outside. Okay, these are the points. And the idea is that exactly the way that we wrote the cones here, when you pass to similar coordinates, this take the form of a ball. Okay, so then in the interior of these cones, then U tends to the bottom block, and the idea is that both of them, they are not zero. So if they are not zero, and you know that U converges to the bottom block, then if you take the quotient, you can prove it goes to 1, since they are not zero. But then outside these cones, both of them, they tend to 0. So then if you take the quotient, it's difficult to, it's impossible to prove it tends to 1. So outside in cones, we used the global Ragnar principle. That means that we managed to put to trap U between two barren blood solutions. So then with that estimate, we are able to bound this quotient and to prove the quotient converges to 1. So this is the proof that the global Ragnar principle is really useful in order to prove this convergence in relative area. Okay, so this is all that I wanted to explain about the global Ragnar principle. And we have a second result that I put in the end. And this result says that if you have a data which is more restrictive, that means a data which is in a space XP that I explained before, but also if this data, it is radial and non-increasing data. So for instance, let's take some data like this. So you should have a data like this and integrable. Then if the radial derivative of the data decays faster than this power of R, which is the radial derivative of the barren blood solution. So if you can control the radial derivative of the data, then you can prove that also the radial derivative of U converges the radial derivative of the barren blood uniformly in the convergence relative. So the quotient converges to 1 uniformly in Rn. This is a stronger result, but it requires much more restricted data. In the paper, we also give some example when the data, it is radial, but it is not decreasing. We can construct something which is not satisfying this hypothesis, and then we prove that the corresponding solution divided by this radial derivative of the barren blood does not converge to 1. Our counterexample is based on the idea that there is a relation between the P Laplacian and the fast diffusion equation. This is something that I will explain to you in the following slides. Okay, just another comment about this formula. So this says that if you require more on the data, then you have the convergence of U to the barren blood also in the C1 topology. So you have a much more stronger. And this is some idea of the proof of the result in this radial data case. This is let's say it is easy once you learn that there is a relation between the P Laplacian evolution equation and the fast diffusion one. And this is the relation. So this is the fast diffusion equation, Laplacian of U to the n. And this you can write it in a radial version, so for radial solutions, and it takes this form here. Now, the advantage to see it in this form is that in this form, you can rewrite this as a weighted fast diffusion equation with a Caffarelli-Cornini weights, and they have this one here. Okay. So now there are previous results proved for all this equation. For instance, for this one, there is a proof of the global Ragnar principle and convergence relative error by Boncourt and Simoneau. And then there is a transformation proved by Jagger, Savinchenko, and Vasquez that says the following, that there is a connection between the P Laplacian and the radial fast diffusion equation. Okay. This is the P Laplacian for radial solutions, and they prove that the derivative of the P Laplacian equation are solutions to the fast diffusion equation. Okay. This is for the P Laplacian, and this part is for the fast diffusion. Okay, so we have a connection between this. Okay, and then we apply this result of Boncourt and Simoneau. We prove convergence in relative error for the solutions of this weighted fast diffusion equation. So then this U will be radial derivative of the P Laplacian, and this is will be the radial derivative of the barren blood from the P Laplacian. So then we recover the result that I explained to you before. Okay. So this is the reference, and this is my grant, they say that I have to put it in all my talks. And this is all. Thank you very much.
Thanks a lot, Diana. Questions or comments? Please.
How about the sign changing solution?
We don't know about fine-tuning solutions. We only did positive, but yeah, I'm not sure if it's even true.
Sign changing solutions have the problem of
What happens?
making questions, right?
Yeah. Yeah.
So the formulation has to be changed.
But also the location of the zeros, you don't know. So you really, this is why, for example, for the gradient, we also have that it has to be radial. The radiality is not really important, but you want to make sure that the maximum is at zero. So the gradient is zero only there, and then you can do the quotient. And so you say, it is a proper zero, which is like a bar, no? But if they start to change sign, you don't know where the zeros are. So what do you take as a quotient below, right? If you take the Barenblatt, it will be plus infinity immediately.
Other comments? Diana, as concerns these results for convergence of derivatives, can you also deal with time derivatives? Okay. Not speed derivatives. Under some assumption.
We didn't think about it. So I don't know.
I see.
Next page.
Okay.
Next page.
Okay,
page.
that's great. Anyone else? If not, thanks again, Diana. You tell us about the timing now.
Yeah, now there is the coffee break. And since we began 15 minutes late, I say, let's begin 10 minutes late. Okay? Okay. And if somebody needs to come up to sign, still, please.
Pues que el denominador puede ser cero y el denominador no. Por lo tanto, en cuanto te equivoques en la posición de cero. Los ceros no coinciden, arriba no es cero y abajo sí. No tiene todo lo que no sea por la base que está después.